Fantastic. All right. So yeah, I have been asked to present Pascal's triangle, which is an exorcism solution. So just to quickly introduce myself, I am Nick. I'm from Alembic. I joined Alembic last year, so I'm probably one of the newest people. So other than Robert, of course. Um, so um, for those of you, I'm sure you're probably all aware of what Exercism is, but if you're not, it's just this great learning resource where you can go and solve very kind of job interviewee type problems. So Pascal's triangle being one of them, and there are different language tracks. So I've done this in the Elixir track, considering I'm speaking Elixir Australia. And your solutions get reviewed by mentors, so you can sort of have real humans actually look over your code and give you feedback, which is awesome. So Pascal's triangle. Again, I'll go over it really quickly just for context. So it's basically a mathematical structure where each row is a function of the previous row. So if we take, for example, the third row here, to calculate each number, what you do is you take the sum of its two kind of parents. So the middle number 2 here, we get that by summing the 1 to the top left and the 1 to the top right. And that pattern repeats. So then in the fourth row here, where we've got a number 3, that's the 1 and the 2, gives you 3, and so on and so forth. So I think that's pretty clear. So that can continue infinitely, basically. So you can take Pascal's triangle to as far as you want it to go. There's a number of useful applications, which again, don't really have time to go into, but notably, the numbers in Pascal's triangle are actually the binomial coefficients for the mathematically minded amongst you. So what you'll find is this is kind of like the choose function when you're talking about combinations. So if you're interested, do some Googling, or if you already know it, cool, you're a maths nerd like me. So the problem on Exercism is basically this: compute Pascal's triangle up to a given number of rows. And so here are some example inputs. So you can see we're just kind of representing the triangle as a two-dimensional array. And so each array within the kind of main array is a row. So for the third row here, for example, you can see your 1, 1, 1, 1, 2, 1, etc. Cool. So I should give a little bit of context. I'm actually filling in for James, who is also from Alembic, who conveniently ended up on leave this week, on holiday, I should say. So I have had to fill in for him. So what I thought I'd do is I'd quickly show you James's solution, and then I'd show you my superior solution, and we could do a bit of a comparison. So this is the code for James's solution. Pretty neat, pretty tight. So I'm going to walk through it line by line. We start with the main kind of public interface, which is the rows function, and that takes in a number. So we want, row 5, Pascal's triangle up to 5 rows, we'd pass it in there. So James starts his solution by calling this function called make rows, and he starts with the first row, which is number 1, and he subtracts 1 from the number that we've passed in. So James's make rows function does a bunch of things. So again, I'm going to step through this pretty quickly, but we'll go line by line. So the first thing that his solution does is it grabs the previous row and it chunks it in groups of 2. So you can kind of see where the solution's going. What he does is he takes the previous row, he chunks it in groups of 2, and he iterates 1 each time. So that's what these arguments here mean. So 2 is how we group the array. 1 is how we step through that array, and discard just basically means we're going to discard any additional elements that don't fit into the groups of 2. In this case, that won't be a problem. So already I can tell you that's unnecessary. So there's my first dig at James's solution. Then what he does with each of those pairs of numbers is sums them, basically. So he's got sum from the enum module. The last thing that James does is he recursively calls make rows, and he sticks a 1 on each end of his new summed solution, and then appends that to the beginning of the array, and then calls recursively with n minus 1. So obviously when you're using recursion, you've got to have a base case. And so James's base case is this. So when we call, when we reach 0, when n reaches 0, we pattern match here. What he does is he reverses his kind of main array, and lo and behold, he ends up with Pascal's triangle. So that's James's solution. I guess I haven't done this kind of talk before, so I'm not sure whether I just kind of speed through or take questions, but I think I'll speed through. And if anyone has questions, they can ask at the end. So quick analysis of James's solution. It has ON complexity, which is nice. It's going to scale really well. It's kind of just recursion for each row, so that's cool. And that's time complexity, by the way, not space complexity. I didn't analyze the space complexity. And he passes all the test cases, so that's great. Now, onto my solution. So this is my solution. Already you can see it's much simpler. No, not really. It's probably pretty similar to James's, but I'm going to talk you through it as well. So it's kind of like almost like an iteration on James's solution. So this is my main entry point. So rows for number, anything other than 1. So the first thing that I do, which is a little bit different to how James did it, the first thing that I do is I actually recurse straight away. So I calculate all the previous rows by subtracting 1 from number. And so what's going to happen is each call is going to keep decreasing number, blah, 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 from n all the way down to 1. Now, when I reach my base case of 1, what I do is I return that initial array of 1. So this is kind of where the difference between James's solution and my solution becomes a bit more obvious. Then I pop back up here. So I've hit my base case, and now I'm coming back up the stack of recursion. Then what I do is I construct the current row by taking the last subarray of the previous rows. So if you can kind of think in your head of that 2D array structure, I'm taking the last element of that array, and I'm sticking a 0 on the front for convenience, so that when we do our chunks, we don't have to do any kind of tricky adding extra elements. Then I do the exact same thing that James did. So I chunk that new array in groups of 2. And iterate 1 each time. So you can think the first 2, the second 2, so on and so forth. No need to discard the last elements. You can totally leave them in. And then I do the exact same thing as James again. I just sum each of those pairs. The final step is just to append the current row to the previous rows. Now, the reason I've got square brackets around the current row here is because, again, we're working with a 2-dimensional array here. So if I just were to stick current on the end of previous, what you would get is you get all the numbers in the current row smooshed into the previous, into the array of rows. So that's not what we want. We actually want to add an array into this array. So hopefully that makes sense. Fantastic. Quick analysis, exactly the same as James. So I won't dwell on this slide. ON time complexity, fantastic, and passes all the tests. So time to unveil the winner. This is the moment of truth. Whose do you think wins? Turns out neither. It's actually this solution that I found on Exercism with the most stars, and it is awesome. I really love it. So I'm going to share it really quickly, even though it's not my solution. So it's by a guy called Bob's Blog, I think, or something. I've got his name in the links at the end. So how he does it is he uses streams, which is really, really cool. So basically, for those of you who don't know about streams, what a stream is it's kind of like a numerable that's generated, right? So what's happening here is we've got our starting element, which is 1. So that's the same as James in my solution. We start with that for that top row. And then the second argument that we're passing to iterate is actually a function that's going to generate our list items as we iterate, right? And then we're going to pipe that to enum take. So we're taking from this stream, we're going to take num elements. So num being however many rows in Pascal's triangle that we want. So funnily enough, the function that generates the next row is exactly the same as the way James and I implemented it. So we take in the previous row, which is going to be passed in by the iterate. We stick a 0 on the front, we chunk it in 2s, we sum it up, and we return that. So this is a really elegant solution, and I really like this. So ultimately, I think this solution wins. And it's not surprising considering it has the most stars on Exercism. Thank you. That's the end of my presentation. Nothing else to say. Here are the links.
Awesome. Thanks very much, Nick. Did you end up submitting it to Exercism for and sort of to get any feedback?
I did not, no, because I only did it very recently, so I should do that.
Cool. Has anyone else done this solution themselves? Or does anyone else do Exercism?
I can't remember if I've done this one, but I have to say that looking at other solutions on Exercism is a great way to find different ways of doing things that you might struggle over. So yes, by all means, look at all different solutions. You find lots and lots of little gems in there. It's a very good way to learn.
Yeah, I particularly liked the stream solution. That was the most starred one. I thought that was awesome.
Hey, Nick, how did you determine the time complexity?
By thinking about it, I guess.
I have a feeling that your solution might not be linear.
Okay. How's that?
Because I think you were appending to the end of the list.
True. Yes.
So you'd be traversing it twice.
Yes, right. Okay, fair enough. So mine would technically be ON squared then?
I think so.
And so if I stop showing my screen, I can pull up my solution again quickly if we've got time.
Matches the screen. Screen queen.
Thanks, Siri. I'll quickly share my solution again. All right, so this was not my solution. This was a really nice one. All right, so that was my solution. So which part are you saying, Josh? Are you talking about this
last line?
Yeah. Yeah, sure. Okay. I suppose you're right. Yeah.
That's why James reversed his, I think. Also, another question while you're pondering that. What was the third argument to chunk every?
So the third argument determines the behavior of what to do when you've got leftover elements. So the best way to demonstrate it would be to actually demonstrate it. But basically what's going to happen is if I want to chunk in groups of 2, and then I've got like let's say I'm chunking in groups of 2 and I'm moving 1 along the array each time, right? When I get to the last element, I don't necessarily have 2 to fit in the last chunk. I've only got 1 because I'm going to move the point in the array to the last element, and I'm only going to have 1 in that chunk.
Yep, makes sense. I understood the discard, but what was the 0 in the list on the last solution?
Where are we here? The 0 is just going to pad it with zeros, right? I don't know. I don't know the specific details about that, but I'm fairly sure that it will just pad it with zeros. When I tested it, that's what it looked like.
Yeah, that makes sense. So it's padded on both ends with zeros.
Yeah. I think it'll just be on the end actually, because
well, you've added one to the front.
Element, yeah.
There's one on the front on the first line.
Oh, sure. Yeah, up in the top line here.
Makes sense now. All right, thank you.
No worries. Any other questions or comments?
I think James was n squared as well, by the way.
Oh, really?
He was adding to the end of the list.
No, I think, you know what? I think I've been undermined here. I think that, oh no, he was too. Yep. Yes, he was. I'm going to blame James for the analysis because we sort of discussed this. So I'll dodge that one.